we're going to do a lab where we're going to try to verify the law of conservation of momentum in a one-dimensional collision. We're going to take a couple dynamics cards, collide them together several times, several different trials, and use that data to plot a graph, which will ultimately show us, hopefully, that the law of conservation of momentum, which I taught you the other day, remember PI equals PF? The law of conservation of momentum is valid. Here's how we're going to do it. First, of course, we write down a problem. That problem is always phrased in the form of a question. What are we trying to show here today? What are we trying to show? We're trying to see if momentum is conserved in a one-dimensional collision. Somebody give me a problem phrased in the form of a question here. What I just said, essentially, phrased in the form of a question. Typically, you're going to have to write this problem yourself, but since this is the first actual lab, we'll kind of work on this one together today. What's the problem phrased in the form of a question? Remember what I just said. We are trying to see or to show if momentum is conserved in a one-dimensional collision. All you got to do is change what I just said into a question.
Will the law of conservation of momentum?
Okay, so that's a good question. Good problem. Will the law of conservation of momentum hold in one dimension with the collision of two cards? Good. Okay. The way that I phrased it, a little bit different. Okay, you phrase it that way, that's absolutely fine. The way that I phrased it here, is the law of conservation of momentum valid for the collision of two dynamics cards in the one dimension? That's pretty much the same as what you said, right? I'm okay with either one of those. Here's a problem that is not a good problem. And this is what I see sometimes. Some people will say, how do we test if momentum is conserved in one dimension? That's not what we're trying to do. We're not trying to see how we test this. We're trying to see if it's conserved. Okay, some people will say, is it possible to see if momentum is conserved? No, that's not the problem. We're not trying to see if it's possible to see if momentum is conserved. We're trying to see, is momentum conserved? So we're going to say something like this. Is the law of conservation of momentum valid for the collision of two dynamics cards in one dimension? Three sets of variables, of course. Manipulated variable, the responding variable, control. How many manipulated variables we got? Always one manipulated variable, and that should become fairly clear to you as we go through this little pre-lab and as you work on the lab with your partners. How many responding variables we got? One. Now, sometimes there's different ways of expressing the manipulated variable or the responding variable, right? Remember we did I think it was a quiz where the momentum was being varied. That was our manipulated variable. But the way that the momentum was varied was by changing the mass and or changing the velocity. So if you could have said in a situation like that, well, the initial momentum is the manipulated variable, but the momentum could have been changed by changing the velocity. So you could have said a velocity was a manipulated variable there as well. It's not like we got two, right? They're just two different ways of stating essentially the same thing. One manipulated variable, one responding variable, and we have like 1,000 control variables, right? In the practice lab that you guys worked on, there were two really important control variables. There are also two really important control variables in this one. That won't always be the case. The magic number won't always be 2. The magic number is, well, however many we absolutely need to control. I'm not looking for the temperature here, the humidity. Like all of that stuff theoretically in any lab should remain constant from trial to trial, but realistically, that's not going to change things, not dramatically enough for us to notice. We're looking for the things that if we change this, it would mess everything up. Does that make sense? Talk about that with your partners, with your group, as you're doing the lab. If we were to change this, oh man, everything is completely messed up. Decide on your control variables with your group members before you're finished collecting data. Okay? That way, when you go to write this up, it's easy. Here's what the procedure is going to look like. And you don't need to write out a procedure for this. I just want to explain to you what you're going to do with this, okay? You're going to take two dynamics cards, a red one and a blue one, and you're going to put them on a track. You see the tracks up here? You guys did this last year, right? Except last year in Physics 20, you only ever used one dynamics card in a particular experiment. We're going to call the red dynamics cart number 1, and we're going to call the blue one number 2. That's going to be the case for all of you. Every group is going to call the red one number 1, and every group is going to call the blue one number 2. You can see the masses of these are labeled. I don't know how well you can see it actually from where you are on the board here, but you'll see it when you actually open up the boxes with the carts in there. The masses of them, the masses are on there. So you need to know the masses, but you don't need to go measure the masses because it's printed on there already. You're going to want to record those masses. Okay, that's important. Those masses are going to be important. Notice that there's also an additional mass put on cart number 1. You're going to do that as well. I don't care what mass you put on there. You decide what mass you put on there. Please don't put something like a kilogram. Put one of the smaller masses on there. But the bottom line is we want cart number 1 and cart number 2 to be, they're not exactly the same mass to begin with, but we want them to be more than a few grams off, like 50, 100 grams off of one another. So that's why we'll want you to add a mass to cart 1. You don't need to measure the mass of that either. If you take one of the masses from the boxes up here, you'll see it printed on there. This one's 200 grams. So if the red card is 274 grams, now my mass would be 474 grams. Make sense? I don't care what it is. Just don't use like a mass of 1 kilogram mass, and just make sure that you record what it is. Now, cart number 2, I should say, the blue one, in each trial will start with an initial velocity of 0 meters per second. It's going to be at rest. Every single time that cart number 2 is going to start at rest. Okay, that's essential to the way that we do this procedure, that one starts at rest for each trial. Now, cart number 1, we're going to give it a push. So it's going to have an initial velocity of something. I don't know what it is, but it's going to be something. So we give cart number 1 a push. It goes toward cart number 2. It's going to collide with cart number 2. And because of Velcro on cart number 1 and on cart number 2, they're going to stick together and head off as one. So cart number 1 moves towards stationary cart number 2. Cart 1 and 2 go off as one. That's like questions 1 to 3 on our worksheet. Remember that? Right? All 3 of those, we had a collision where the 2 objects stuck together and headed off as one. That's important. If they don't stick together, that might happen. They don't stick together because the Velcro doesn't quite work out in a particular trial or something, then that trial's no good. You've got to throw away that trial and do it again. Now, that's trial number 1. Trial number 2 is just, hey, give cart number 1 a push so that it's got a different velocity. That's all. We want a different initial velocity or a different initial momentum, really, is what we want, right? And then trial number 3, well, cart number 1 is going to have a different initial momentum. And then trial number 4, it's going to have a different initial momentum, and so on and so on and so on and so on. Good? How many trials do you think you should do? Yeah, usually you do 10 trials. Usually you do 10 trials. All right. How do we collect the data? You guys have used this SparkView app in the past several times. It's going to work at almost the same today as it's worked in the past, but there's a couple of tiny little differences. We're going to go through this just to remind you of how it works because it's been a while for all of you, and because there is a couple of tiny little differences from the way you did it last year. When you click on that SparkView app, it should take you to this screen. I want you to click on Sensor Data. And that's what you did last year. That's what you can do this year. You are going to connect 2 carts this time. Make sure that it's your 2 carts. One of them is red, one of them is blue. You're probably going to see 6, 8 carts listed, depending upon the proximity of you with other groups. You want to make sure that you click on and connect your 2 carts. You don't want to be using Ryan's cart to collect your data because it's not going to be consistent, right? So you want to connect your 2 carts. And last year, every time you collected data, you clicked on this position box. You're not going to click on that position box. This time, you're going to click on the velocity box. So remember that. Okay, when I'm walking around and you guys are working on this lab and I'm helping you guys out, some of you are going to get graphs that look all wonky. and it's going to be because you click on the wrong box or clicking on position. It's not wrong technically to do that, but you will not see what you need to see. It will collect all of the relevant data, but you won't see the data presented in a way that makes it easiest to determine what the data is. So click on the velocity box, but you're going to actually have to do that twice because we have two cards. So last year you clicked on position once. Today you're going to click on velocity twice for each different card. And then you're going to click on the template that you want to display. I want you to click on the one that says table and graph. Display the table and graph. Make sense? So sensor data, make sure you connect your two cards and make sure you select velocity to display the velocity. And then you're going to connect, or select, I should say, the table and graph to display. When you do a trial, it should look something like this. Now let's take a look at the graphs that we see here. Graph number 1 represents the red cart, and that was cart number 1. The blue one is cart number 2. So cart number 1 is pushed toward cart number 2. And then it collides, and then they head off as one. Nothing's happening initially, right? We're collecting data here before it was pushed. You remember when you did this last year? When you pressed the start button, there was a little bit of a delay before it actually started collecting data. It's a good idea to press the start button, wait for it to start collecting data, and then give it a push. But when you do that, sometimes you're going to get a little bit of non-motion before you're actually starting to collect data. That's fine. Don't worry about that. What's happening? You guys tell me what's happening right here. What's happening right here? See, velocity of 0 meters per second and then negative? Negative velocity? Yeah, go ahead. Yeah, you know what? It just means because of the way the carts record data, it's actually based on the motion of the wheels. So if the wheels are spinning in the direction that is defined as negative, then it just makes it a negative velocity. I don't care about that. Okay, if your blue one is negative and your red one is positive, if your red one is negative and your blue one is positive, I don't care about that. Take the magnitude of that velocity, okay? You can see that the velocity is increasing in the negative direction. This is when I'm pushing it, right? As I push it, the red one speeds up, right, as I push it. And then when I let it go, it's moving at this speed. That's the maximum speed that it's going to be, right? When I let it go, that's how fast it's moving. And then what happens? Well, it collides with the blue one. How do we know when it collided with the blue one? Look what happens here with the blue one. Look what happens with the blue data. Not moving, not moving, not moving. Oh, look, now it's moving. That's when the collision took place, right? The collision takes place when the blue one starts moving. Now, we're going to record VI for the red cart, and we're going to record VF for both carts combined. You're going to look at these graphs to see if you have good data. You're not going to actually read anything off of these graphs. So look at these graphs. If you see more or less these shapes, red one looks like this, blue one looks like this, then you have good data. Go to your table now. Let's look at our table. Chart number 1, the red one, negative 0.233, 0.389, 0.530, 0.601. Look, the red one's speeding up, right? Look at the blue one, 0, 0, 0, 0, right? The red one is speeding up, the blue one's not moving. Oh, wait, the red one is 0.595 and the blue one is starting to move. That's where the collision took place. Does that make sense? That's where the collision took place. What am I going to say is VI? The velocity immediately before the collision. My VI here would be 0.601. It says negative 0.601 there, but we're going to record it as a positive value, right? Does that make sense why it's 0.601? The collision took place at data point 47. So my initial velocity is the velocity immediately before the collision took place. Do you see why it took place at 47? Because that's when the blue one started moving, right? So the initial velocity will be 0.601, the velocity just before the blue one started moving. You're just going to write that down on a piece of paper. Last year, most times you had to export data. You don't have to do that today. You just have to write down VI on a piece of paper. Oops. Now, what about VF? What about VF? The velocity immediately after the collision. Take a look at this table now. The red one is slowing down. Look, of course the red one's slowing down. It's colliding. The blue one is speeding up, 0.191, 0.300, 0.356. Of course it is, right? It was at rest. It has to speed up to take off, right? We want the velocity immediately after the collision is finished. When is the collision finished? When they're both moving at the same speed. Look at this. Actually, let's see. Yeah, 0.366, 0.35, 365. Sometimes it's a little ambiguous exactly which one we should pick, but they're going to be very close. Use your judgment on that. At this point, they're both moving 0.365 meters per second, which means they're both moving at the same speed. They're heading off together as one. So we're going to say the final velocity is 0.365 meters per second. 0.366 could have worked as well. You could have chosen to include that one as well. So that's going to be VF. VI in this case, 0.601, VF, 0.365 meters per second when they both become the same. Now we're going to record that. You're going to have already recorded the masses, right? Including the mass you put onto the red cart. You're going to title this table. Title might be just something as final velocity of two cars as a function of the initial velocity of the first car, something like that. It's just essentially a word description of what the table represents. And then you're going to record the initial velocity, which was, what did we say it was, 0.601 meters per second. And the final velocity we said was 0.365 meters per second. And then you're going to do it again with a different initial velocity, different initial momentum. And then you're going to see what the final velocity responds to that. You can do that 10 different times. There's the data collection. I'm not going to tell you about the analysis collection yet. We'll wait till you're done collecting the data, and then we'll do the analysis just so that we're not overwhelming you with all this information all at once.